Welcome once again to our latest lecture. This one we're going to start investigating quantum physics. Quantum physics is the other great new idea in modern 20th century physics along with relativity. And it represents a startlingly different way of looking at reality. And it gives us results that are pretty much against the common sense phenomena that we experience in our day-to-day lives. There are some really bizarre ideas in quantum physics. But despite that, the success of the theory has been profound, and we simply have to accept the fact that things that happen in the world of the very small, where quantum physics rules, are just different from our macroscopic day-to-day experiences. Let's get a start on understanding how, from a historical aspect, quantum physics developed. By the end of the 19th century, the physicists of the time were largely thinking that the great questions were answered. It was simply a matter of getting more refined constants, exactly how many digits do you want in the electrostatic constant of the universe, sort of thing. They had Newton's laws for mechanics. They had Maxwell's laws for electromagnetism. In the world of thermodynamics, there was a collection of contributions from Joule, Clausius, James Clerk Maxwell here, and Ludwig Boltzmann. So those were the major fields of physics. It felt like that there was a very sturdy foundation and that there wasn't anything dramatically new to learn. There were some things that were not so well understood, but it was thought that it was just a matter of tweaking the theory to explain these phenomena. One of them, as we discussed earlier, was the consistently finite and same measurement for the speed of light in all frames of reference. It took relativity to give us a better understanding of that. But quantum physics originated from a few other observations that were thought to be minor deviations in our understanding of the theory at the time, that turned out to be rather profoundly different situations than the theories predicted. Among them, there was this idea of so-called perfect black bodies. This is a thermodynamics concept. Perfect black body is an object that emits light and emits heat and absorbs heat. It emits heat into its surroundings based on its own temperature, and it absorbs heat based on the temperature of the environment. But in a perfect black body, the emission is independent of the absorption, whereas in many day-to-day situations, there's a strong correlation between the temperature of emission and the temperature of absorption. Despite the fact that we don't think of it as a black body, the sun and any other star, those are great examples of perfect black bodies because there's no way that they are emitting energy at a rate consistent with their absorption of energy in the environment of space. Their emission is entirely independent of the absorption, and they are, despite their brightness, considered perfect black bodies. Another phenomenon that was annoying at the time was the illumination of metals with light could cause the metal to start emitting electrons. Maxwell's theory predicted this would happen, but measurements and experimentation showed a discrepancy between what the theory predicted and what reality was demonstrating. And another point of contention was when you take an element and you get it into gaseous form and you run an electric current through it, the gaseous element will start to glow. But what was found was that there was a very characteristic signature for each element. It was expected that each element would emit an entire spectrum of light, but the findings were quite different. Nevertheless, despite these discrepancies, it wasn't thought at the time that these were heralding a new understanding of physics. Yet, turns out that they were. Black body radiation is, as I said, a thermodynamics concept. You can talk about a perfect white body, which is a perfect reflector of all of the heat that comes onto it. It just simply emits heat at exactly the same rate that it is absorbing heat, and its temperature is exactly that of the environment surrounding it. A perfect black body, the temperature of the body itself is independent of the surrounding environment. Maybe they are the same, but that's a coincidence. The perfect black body emits heat based on its own temperature and doesn't emit heat in any way influenced by the rate at which it absorbs heat. The predictions by Maxwell's theory for black body radiation were quite specific. Maxwell's theory said, yep, they will emit light. They will emit heat. There was no problem with that very general idea. But it was the way that they were emitting light and heat that was bothersome. Maxwell's theory said that black bodies would emit light of all wavelengths, and to a good approximation, they do. But Maxwell's theory said that short wavelengths would be more likely emitted. Short wavelengths, for instance, red is longer than yellow, is longer than green, is longer than violet, is longer than ultraviolet. Maxwell's theory said that there ought to be a lot of ultraviolet light emitted by perfect black bodies. But that's not what was found. It was found that perfect black bodies tended to emit very little ultraviolet light. And this discrepancy was kind of hyperbole to say that it was called the ultraviolet catastrophe. It was kind of called that tongue-in-cheek. Thought, well, we just need to tweak the theory and our understanding. Turned out it was a lot different. If you look at the emission spectrum of a perfect black body, they all have the same general idea in that if you plot the intensity on the vertical axis and the wavelength on the horizontal axis, very, very little light is emitted at long wavelengths, and at extremely short wavelengths, very little light is emitted. There tends to be a peak wavelength and range of wavelengths around it at which you are most likely to find emitted light. The temperature of the black body affects the location of this peak. So the purple curve represents a hotter surface, then you have the yellow, less hot, and the red curve representing a cooler surface. There's still the same general approach that there's very little light emitted with very long wavelength, and there is zero light emitted at short wavelength. The prediction of the location of the peak wavelength as a function of temperature was made by Wilhelm, Karl, Werner, Otto, Fritz, Franz, Wien in what is now known as Wien's law. The maximum wavelength emitted in that intensity distribution times the temperature in kelvins is equal to 0.002898 meters times kelvins. Wien's law is strictly experimental, strictly empirical. Wien did not have any deep theoretical calculation. He just noticed this trend in the value of the wavelength for a given temperature of a black body, and he said, well, look, all of these points fit this relationship. If we apply Wien's law to the sun, the peak wavelength of the sun is at about 500 nanometers, which is in roughly the yellow part of the spectrum. But there is a range of wavelengths around it. It is not strictly yellow light and no other kinds of light. But the peak is at about 500 nanometers. If we apply that to Wien's law, we can find the temperature of the sun, the surface temperature anyhow of the sun, 0.002898 divided by 500 times 10 to the negative 9. We get a result of 5,800 kelvins, which is a pretty good approximation of the surface temperature of the sun. You might have seen a stovetop burner in an electric stove. The coil itself, when it's cool, has a dark grayish color to it, but when you flip the control on to high, it obviously starts to warm up. And as it starts to warm up, it gains a deep red color. The red becomes stronger and stronger, and as it gets hotter and hotter, you'll even see it start to turn somewhat orange. What's happening is the peak wavelength of emission is getting shorter and shorter, and as it gets shorter, it's more likely to start including wavelengths shorter than red light, and that means it'll start including orange light. If we could let this burner heat up even more beyond what kitchen safety would normally allow, we could imagine this burner becoming white hot or even bluish hot if the temperature gets that high. This is exactly what happens in stars. Stars obviously are not bound by kitchen safety rules, and the surface temperature of a star is roughly indicated by the color of the star. Reddish stars like Antares have relatively cool surfaces. An orange star like Aldebaran, if you take a look at the handle of the Big Dipper, and if you imagine following that curvature around, you will run into an orangish star, that's Aldebaran, and it is hotter than Antares. You get to an even hotter surface star like the Sun, which is basically white hot, and then if you were to crank the temperature up even higher, you would start getting even a bluish white color, and that's what you find in some of the hottest stars in the sky, like the star Sirius or the star Vega. Those surfaces are so hot that the star appears bluish white. The discrepancy between Maxwell's prediction and the experimental results was non-existent for long wavelengths. Maxwell's theory did a great job with the long wavelengths. It was these short wavelengths. When you start getting into the short wavelengths of the visible part of the spectrum and into the ultraviolet part of the spectrum, that the discrepancy was becoming beyond obvious. So there was this ultraviolet catastrophe. Oh my goodness, how do we explain this? And it was one of those bothersome things. It was thought, well, all we need to do is tweak the theory. Well, it took more than tweaking. If we take a look at this simulation right here, we can get a little bit of a clue as to how the plot of intensity versus wavelength can change with temperature. You see the temperature on the far right. The nominal temperature of the black body is 7,250, and you can see that the peak of the curve is pretty close to the violet end of the visible part of the spectrum. If I decrease the temperature, you will see that the peak is now more like in the yellow or orange part of the spectrum. So as we decrease the temperature, it also becomes cooler and just simply emits less light, whereas if we increase the temperature and it becomes hotter, we also see that the peak wavelength gets shorter and shorter, and we see at 8,050, for instance, for the surface temperature, that the peak is actually just into the ultraviolet part of the spectrum. Around this time, there was a German scientist by the name of Max Planck, who was taught at the Technische Universität München, Technical University of Munich, and his advisor there was telling him, you know, physics isn't the place to go. All the good problems have been solved. Go pursue something else. But Planck stuck in physics, fortunately for us, and the idea of the discrepancy in black body radiation caught his attention. And in 1900, he published a paper of his analysis. He made an assumption. He said, let's pretend this behavior exists, and then what would be the mathematical consequences? And when he figured out the mathematical consequences, he came up with a mathematical equation that described the shape of the experimental curve exactly. So he gave physicists of the time an equation. Look, this equation works. If you can figure out how to tweak Maxwell's theory to achieve this equation, then we have this problem figured out. What Planck did to generate that equation, the assumption he made was something he didn't believe was actually happening. He thought, well, let's just pretend that this is happening, see what the mathematical equation results, and hey, it agrees with experiment, but what he assumed he didn't believe was actually taking place. What he assumed was that light, instead of being emitted in a continuous spectrum of values, could only be emitted at very specific values. It could be emitted at this value or that value, but not at any values in between. These discrete values he called quanta. And when I say discrete, I don't mean can keep a secret, so you can see what we mean by discrete in this context. So Planck said we can have light of this frequency and we can have multiples of this frequency. And if you do that, and if you go through the math, you get the expression that describes the experimental results. Ultimately, Planck won the Nobel Prize in Physics for this, despite the fact that he didn't believe it was actually happening. He said that in order to determine the numerical values of the allowed energies, you need to introduce a multiplicative constant. This multiplicative constant he labeled lowercase h, and it is now known in his honor as Planck's constant. It's equal to 6.26 times 10 to the negative 34 in standard units of joules times seconds. The incredibly small value of Planck's constant allows us to say that it looks like the energy emitted is continuous, but if we have Planck's constant as our multiplicative factor, a difference between 1h and 2h is indistinguishable in a macroscopic scale. But in this very tiny microscopic quantized world, it is a significant difference. Planck didn't believe it was actually happening, but he said, listen, if we quantize the emitted light, we get the equation we need. It looks like it's continuous, but it's just so finely divided because Planck's constant is so small. The divisions between them are so small, and it looks continuous, but it's not. So Planck came up with this idea, said, look at this, kind of funny, here's the equation, but you don't have to believe this is actually happening. However, in 1905, just 5 years after Planck published this paper, someone did take him seriously, and that someone was, of all people, Albert Einstein. Einstein took Planck's idea and applied it to a different phenomenon whose understanding was not within the realm of the classical physics of the 19th century. This phenomenon was first found by Heinrich Hertz. If you'll recall, Heinrich Hertz was the German experimentalist who showed that Maxwell's prediction that light was composed of electromagnetic waves was true. In the process of exploring that possibility, Hertz discovered something that is now called the photoelectric effect. The photoelectric effect might be one of the most literally named ideas in physics, the photo meaning light, the electric meaning electron. And the photoelectric effect is what happens when you shine light on a metal. If you shine light on a metal, that metal might start to eject electrons. But notice I said might. The metal requires the light to have a minimum frequency. If the light is below this cutoff frequency, the metal will not emit electrons. If the light is above this cutoff frequency, then yes, the metal will emit electrons. And different metals have their own cutoff frequencies. It's not like the same cutoff frequency applied to aluminum and to iron and to gold and to silver. There was one cutoff frequency for aluminum, another for iron, another for gold, another for silver, so on and so forth. So that's the phenomenon, but the theoretical prediction was a bit different. The theoretical prediction could perhaps be visualized by a rock near the ocean. and ocean waves come in and batter the rock, and over time the rock erodes. So pieces of the rock are effectively ejected into the water. And this will happen even if the water washes over the rock once every few seconds. If it was only once every few days, if it was only once every few hundred years, if you wait long enough, you will see erosion in the rock. That was Maxwell's prediction. Light waves would erode metal, and the erosion would be in the form of electrons being ejected out of the metal. Well, that was an issue because there had to be a minimum frequency in order for the electrons to be emitted in the actual experimental results. Another issue was that in Maxwell's prediction, brighter light, more intense light, would cause more energetic electrons, and that wasn't found. There were more electrons emitted, but they did not have more energy. So brighter light above the cutoff frequency creates more electrons, but they don't have any higher energy, and that went against Maxwell's theory. So a couple of issues there. Einstein had read Planck's paper and was intrigued by the idea. And he decided, let's take Planck's idea of quantities being discrete and apply it to light and apply it to the photoelectric effect. He basically said, let's treat light as particle light. Now imagine that you have a wall and you throw a Nerf ball at it. That Nerf ball is not going to have enough energy to chip the wall. But if you had a gun and you fired a bullet at the wall, obviously there would be some chips spraying out from the wall if you shot it. Einstein said that the frequency of light affected the energy. And so a Nerf ball is the equivalent of a very low frequency, low energy particle of light, whereas a bullet fired from a gun is an example of a very high frequency, high energy particle. And so the higher the energy, the more likely you're going to get some erosion from the wall. Now, this was quite annoying at the time because it had been settled by Maxwell and by Hertz's experiments that light was wave light, but Einstein's idea took hold, and ultimately Einstein won his Nobel Prize, his one and only Nobel Prize, despite all of his contributions. He won only one, and it was for the photoelectric effect. So Einstein says light comes in particles, and these little pieces of light, these little particles of light are called photons, and the higher the frequency, the more energy these particles have. And what we need is enough energy to dislodge an electron that is held by the metal. The metal has a whole bunch of electrons in it, and the electrons want to stay in the metal, but if a photon with enough energy comes along, it dislodges that electron from the metal. And that was Einstein's explanation for the photoelectric effect. Einstein developed this idea of a cutoff frequency and said that each metal has its own so-called work function. The work function is basically the minimum energy that holds on to an electron in the metal. Some electrons are more tightly bound. It's a statistical thing. The work function is the energy used to bind the most loosely bound electron in the metal. The value of the work function is a few electron volts. You might recall the issue of electron volts from the previous class. 1 electron volt is equivalent to 1.6 times 10 to the negative 19 joules. And so a few electron volts is still on the order of 10 to the negative 19 joules. And that's a typical value for the work function, according to Einstein. The ability of an electron to hold on to, the ability of a metal to hold on to the most loosely bound electrons is the work function. So an electron volt, how does it get its name? It is the result of one electron passing through 1 volt. An electron has a charge. If I let the electron drop, quote unquote, drop through 1 volt, if it starts from rest, the electron will have electric potential energy converted into kinetic energy. And the amount of energy is the charge of the electron times 1 volt. The charge of the electron, 1.602 times 10 to the negative 19 coulombs times 1 volt, gives us this conversion factor. 1 electron volt equals 1.602 times 10 to the negative 19 joules. Please try to not be confused by situations where we talk about the charge of a proton or an electron, which is 1.602 times 10 to the negative 19 coulombs, and when we talk about energy at these scales, 1 electron volt, 1.602 times 10 to the negative 19 joules. It's confusing. So we'll use electron volts here and there. Just remember, electron volt times 1.602 times 10 to the negative 19 gives you the energy in joules. 1 electron volt is not a lot of energy on our scale, but it is a significant amount of energy if you're an electron. Einstein said that if we see the photoelectric effect take place, it's because the energy of the photon striking the metal is at least equal to the work function of the metal. So the energy of the photon, which, by the way, a photon is often called a gamma ray, and so you will frequently see a photon represented as the lowercase Greek letter gamma. It turns out that the energy of a photon is equal to h times the frequency. And if h times the frequency is at least equal to the work function, then we see the photoelectric effect take place. If the frequency is too low and hf is less than the work function, I don't care how brightly the light is illuminating the metal, no electrons will be ejected from the metal. If you eject an electron from the metal, it's going to have a certain amount of energy. The amount of energy it has is basically equal to the energy of the photon striking it minus the work function. So the energy of the photon, some of it is used to dislodge the electron, and then whatever remaining energy of the photon is used to give the electron its own kinetic energy. So this is how these were measured. If you can measure the energy of the electron, and you can, using our understanding of electricity, then you can start gaining an experimental understanding of what the work function is for each metal. Imagine running this experiment and you shine different frequencies of light on the metal. And then you determine the energies of the electrons that are ejected for each frequency of light. And what you find is experimentally maybe a plot like what you see on the screen. The higher the frequency of light, the greater the energy of the ejected electrons. But once we reach a cutoff frequency for the light, no electrons are emitted whatsoever. And these plots generally fall along a straight line. And if you fit a straight line to the data and you look at where the straight line meets the horizontal axis, this is the cutoff frequency, the minimum frequency that you need in order for there to be the photoelectric effect. And it's from this information that we can get the work function for each metal. Let's suppose that we have that the work function of some metal, some alloy, is 5.27 electron volts, and we want to ask what is the cutoff frequency, and then we want to ask what kind of light is associated with that frequency. So cutoff frequency is the minimum frequency at which we get electrons emitted. The minimum frequency is equivalent to the longest wavelength. The minimum frequency means that the electrons are just ejected and there's really no excess energy. The electrons are ejected and they are no longer associated with the metal, but they basically have zero kinetic energy. It's just enough. That means that the work function phi is equal to Planck's constant h times the cutoff frequency. Now, 5.27 electron volts for the cutoff frequency, we convert that to joules. We get 8.443 times 10 to the negative 19 joules. We get h times this cutoff frequency equals 8.443 times 10 to the negative 19 joules. We can find the cutoff frequency because h is Planck's constant. We take the cutoff frequency in joules, we divide by Planck's constant, 6.626 times 10 to the negative 34, and in this problem we get 1.27 times 10 to the negative 15 times 10 to the positive 15, that's a typo, times 10 to the positive 15 hertz. This is equivalent if we use C equals F times lambda, therefore lambda is equal to C over F. This is equivalent to 235 nanometers, 2.35 times 10 to the negative 7 meters. Or 235 nanometers. I see I made the same typo there. So, 235 nanometers, that's in the ultraviolet part of the electromagnetic spectrum. This is a perfectly ordinary situation for an alloy, a metal, and the photoelectric effect. Nothing unusual about these numbers. Okay. That's enough. We'll discuss the issue of gaseous elements in another lecture. Take care. Bye-bye.